Hello everyone. So in this video, we're gonna try to explain a code of some matches on GPUs, and finally solve this exercise by adapting to integer matches addition and find the best execution configuration. So walking through the code, um, this is the code that we're going to try to tweak on. And basically, this is a code that does a matrix addition and going. This is a the host code by initializing the data in some sort of a random items through a loop, and we have a function where we sum a matrix, and everything is set up on float as we can notice, and we have to change these on to integers that we're gonna do eventually. So this is doing an addition through this loop in here. Then we have a checking result. So here we check the result either if the arrays match or the arrays do not match. And then here comes in the kernel code where we set up the number of threads, blocks, and block dimension. As you can see, they all set up on float again. And here uh, we just check the CUDA device. Here we set up the data size of a matrix. We're gonna set up the data size of the matrix. Here we're trying to deal with the memory of a host memory. This is where I assign the variables of the matrix. We kind of transfer of data, and eventually we're gonna initialize data at the host side. So we're calling that function initialize data. We assign these parameters for the matrix. And here we set up the memory here. We have the memset. And eventually, here with the kernel code comes in, add the matches at the host site for result checks. So here we're calling our function on the host side to see how much that takes, what is the performance of that. And then here we want to set up the global memory with the CUDA malloc, then eventually transfer data from a host to a device. So we transfer the memory from the host to the device with all the matrix parameters, and then eventually this is where we invoke the kernel. We set out the number of x and y's, dimension of x and y's, to create a block and grids. So here we create a block with this dimension of x and y's, and a grid with a number of x and y that is going to match along with the block. So here as well, we calculate before starting the job. We want to calculate how long it's been taking. Here we're calling the function in a host using the kernel, and we set up the grid and the block along with its parameters, and we check device synchronization. And then after finish up, we want to get how long it took, and then we print everything. And here we want to copy the kernel result back to the host side. So we want to get the result back to the host. And here we call this function check result to see if the arrays match or not. When finally finished up, we want to free the memory in the CUDA and then eventually free the memory in the host. So here has been assigned to us to adapt it to an integer and find the best execution configuration. And what we're gonna be doing for that is I've been setting up everything here at this code. So the main target is to switch from float to integers. As you can see here, before you used to be floats. Now we all change those to integers. All over wherever it says float is being converted as integer. As eventually here at the kernel code, when we call this function, we call it with the parameter of integer. So this is solving us the first requirement. Then we want to apply the best practices configuration. So here comes into tweak with a number of threads and kernels. and I switched up here the number of dimension and grid to the need. So now here we're not gonna want to set up an extra threads if it's unnecessary, but we want to go with uh, most adequate number ever. So here I have this code compiled, and we can see it here. So this is the code, and it's been compiled successfully. A little bit here in the top. Okay, there we go. So here it's been compiled successfully, and then here we call it see the output, and here is showing the using device what we're using. We're showing the matrix size and the matrix initializing how long it took to from the host side, and then the same matrix on the host how many seconds it takes compared to the GPU with the kernel that it took very less compared to the host code. And then we have the output as arrays match. So this is resolved as the issue. And so just switching up from float to integer for an optimization purpose, and we have the code running. Now we're gonna back to the second assignment is refer to this code and make a new kernel to let each thread handle two elements and define the best execution configuration. So here, first we're gonna show the code, and actually it's the same, almost the same code. However, what the difference is that is using one grid in here. So the same code, the difference is that it's a one dimension thread block. Now we wanted to this code handle two elements. So I already did the changes in here, and I've documented the changes. So we have two major changes here at the kernel, but we want to ensure that we have the x multiplied with 2 to that be able to each thread handles two elements. Okay, so where that is being changed, if we go here, as you can see, before it was just an x plus block x. Now we divide by 2. Here, but before that, we first set them out in here. So here, when we assign the index to handle two elements, we multiply with 2, and here as well. Again, goes same goes here. So then eventually, here I've documented that in here. When we set up the dimension grid, we just as well again multiply with 2, just right here, right? And this is should be allowing us to thread two elements per thread with one dimension block. Okay, so let's try that. So I have actually successfully as well compiled it, as we can see here, and we invoke it. And again, we have the using device here. Okay, there we go. So, oops. Yep. So we have the device, we have the matrix size, and the matrix initializing how long it took, and we have here the matrix on a host, how much it took, because with a one dimension block, and here look with the thread with the best configuration practices, how long it took in the kernel, which is way too less. Thank you for watching.